Alien life forms. We've all seen them in science fiction. Moon people, Amazon women of Venus, E.T. phone home. From Vulcans to bug-eyed musicians, we've seen a huge variety, conjured up by our imaginations. The fact is, we have yet to find any real life beyond our own planet, not even a microbe. But we keep trying, even though finding alien life is like looking for a needle in a haystack. Just look up at the night sky and you can see the enormity of the situation. Hello and welcome to CU Science Update. I am your host, Nick Sirois. If we scale down the relative size of our solar system to something manageable, Earth would be a speck of sand compared to our grapefruit-sized sun. On this scale, Pluto, the former 9th planet of our solar system, would be about as far as Fisk Planetarium is from the engineering building. The nearest star, Alpha Centauri, some 4 light-years away, would be about the distance to Illinois. And there are billions of stars even further away. So if we're going to find alien life out there among all those stars, we should look for places where life is likely to be found, on planets. Planet hunting is a daunting task. Finding a faint little planet in the glare of a bright star would be like looking for a birthday candle in front of a searchlight. But this stunning image, taken in 2008 by the Gemini Observatory in Hawaii, did just that. It's the first direct image taken of an alien planet orbiting a star some 500 light-years away. The planet is 8 times the mass of Jupiter, the largest planet in our solar system. Direct imaging is one technique to find alien worlds, but indirect observations are used more commonly. One of these is called Doppler spectroscopy, which looks at how light from a star changes when it's being pulled by a nearby planet's gravity. Every planet has a gravitational tug on the star it orbits. This tug makes the star appear to wobble. From Earth, we can detect this wobble by the effect it has on the spectrum of light coming from the star. As the star wobbles away from Earth, the light waves are stretched, shifting towards the red end of the spectrum. As it wobbles toward us, the light waves are compressed, shifting it towards the blue end of the spectrum. The shifts in the spectrum of light are called Doppler shifts. The amount of wobble can also help us deduce the size of the planet. Large planets have more gravitational force, which will have a greater tug on the star. So the greater the wobble, the larger the planet. But if the orbit of the planet is seen from Earth edge-on, then another technique to find it becomes available. Just like when the moon eclipses the sun, blocking out much of the light, an exosolar planet passing in front of its parent star will do the same thing. When this happens, we can see the starlight get slightly dimmer. When the planet moves behind the star, the normal brightness returns. These changes in starlight can be seen using a technique called photometry, which is being used on board the Kepler spacecraft.
2, engine start, 1, 0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Since its launch in early 2009, the Kepler spacecraft, operated by students and professionals at CU's Laboratory for Atmospheric and Space Physics, has surveyed well over 150,000 stars in the constellations Cygnus and Lyra. Ball Aerospace in Boulder built the spacecraft, which includes a photometer, an instrument capable of measuring tiny decreases in the brightness of stars when planets cross in front of them. Since 1988, Doppler spectroscopy and photometry have led to the discovery of over 450 extrasolar planets. Kepler alone has found over 700 candidate planets. Many of these planets are gas giants like our own Jupiter, which is why they're sometimes known as Jovian planets. Our solar system contains 3 other gas giants, Saturn, Uranus, and Neptune. As the name implies, gas giants are largely composed of gas, mostly hydrogen and helium. Their atmospheres are extremely thick. On the surface, if there is one, pressures would be so great that it's unlikely any life could develop and thrive. The goal of the Kepler mission is to find planets that are about the size of Earth and are orbiting stars at a distance that makes them habitable for life. Speaking of which, what makes a planet good for supporting life anyway? For starts, a planet that is capable of maintaining liquid water on its surface. Such a planet would have to orbit the star in a region that doesn't make it too hot where water evaporates, or too cold where it freezes. This region needs to be just right. We call it the habitable zone. In our own solar system, the habitable zone starts about halfway between Venus and Earth and extends towards Mars. The most likely place for us to find alien life would be to look for planets that lie within the habitable zone. Of course, there are exceptions. we might find planets outside of the habitable zone that are capable of providing suitable conditions for liquid water. One example would be Jupiter's moon, Europa. Not much smaller than our own moon, Europa is covered by a smooth, icy crust. The lines and cracks on the surface and the near absence of craters suggest that Europa is geologically active. Tidal stress exerted on Europa by Jupiter's strong gravity could be generating enough heat to liquefy the ice deep below. Thermal vents could warm the water sufficiently to harbor life, perhaps not unlike those we find in the deepest oceans on Earth. Who knows? Europa could be an orbiting incubator for life. This isn't the first time people have speculated on life elsewhere in our solar system. Over a century ago, it was readily accepted that there was an advanced civilization on Mars. Telescopic observations of the red planet showed what appears to be similarities to Earth. There were polar ice caps, seasonal changes in the surface, and what appeared to be canals. Speculations about these canals sparked imaginations. American astronomer Percival Lowell proposed that the canals were made by a very, very thirsty Martian civilization. This idea inspired British author H.G. Wells to write The War of the Worlds in 1897. The Martians, jealous that Earth had all the water, sent an invasion force to secure the resource. Even after the canal theory was put to rest in the early 20th century, people still held out hope for life on Mars. The Viking landers in the mid-1970s carried out experiments to find microorganisms in the soil. Nothing was found. Then in 1996, a team of NASA scientists announced to the world they had discovered evidence of past life on Mars. What appeared to be fossil remains of bacteria were found in a Martian meteorite that had fallen in Antarctica 13,000 years ago. Other scientists have disputed the findings, and the debate rages on. Here at CU, we're still keeping an eye out for extraterrestrial life, including life on Mars. Brian Hynek is an assistant professor in geological sciences and the Laboratory for Atmospheric and Space Physics. He recently made news after publishing a study that shows oceans once existed on Mars. Apparently, Marvin was a pretty good swimmer too. CU Science Update's Marisa McNatt visited Brian to get the red, dirty details on Martian life.
Better telescopes and measurements are allowing scientists to detect and study other solar systems or new terrains where life could be flourishing. However, viewing the backyard of our own solar system remains an easier task. In the search for extraterrestrial life, eyes have been focused on Mars. In the last decade, NASA and the European Space Agency have been sending orbiters and landers to Mars, leading to some surprising clues about the existence of water on its surface.
It might have been the case that Mars was suitable for life before Earth was. There's evidence on the crust and in the geological record that it had large oceans in the past, large lakes and seas, river systems, deltas we found all over Mars. So it seems like there was water around for maybe 500 million years of its history.
And where there was once water, life could have existed, and maybe it's still there.
At the surface, it's pretty harsh conditions. You have no magnetic field protecting it from harmful particles from the sun. It's pretty sterilized, oxidized, but down in the crust of Mars, where water is stable, that would be the place to go look for life at present.
But what kind of life?
Microbial life, so simple life forms like we had on early Earth, are pretty likely in places like past environments on Mars.
Mars is about 40 million miles from Earth. How do we find something as small as a microbe?
Current techniques trying to understand the atmospheres that are around other planets, around other stars, because Earth's atmosphere is heavily influenced by life, and the abundance of oxygen is only because of all the photosynthesizing organisms that we have. So if we find abundant oxygen or ozone layers, or even things like methane, which is a byproduct of a lot of chemical reactions associated with biology, these would be inferences that life might exist on other planets.
NASA's getting ready to send another robot in 2011 capable of driving longer distances over rough terrain.
A large lander that will drive around maybe 15 miles or so across the Martian surface and study the rocks, the soils, and look for signs of a past life in terms of isotopic signatures, in terms of fossils, microfossils, things like that.
The Mars Science Laboratory will explore Mars where no rover has gone before.
life beyond Earth has been asked since humans came about and started to wonder about their own existence. And are we alone has been this question for hundreds of thousands of years, undoubtedly. And we're actually at a place now where we can begin to address that and scientifically and look for signs of life on other planets. And so we have the technology and the scientific understanding to go out and maybe answer that question. So it would mean something different to everyone if we found life on Mars or under ocean on one of Jupiter's moons. To me, it'd be really exciting to be here at this time when we can answer one of life's oldest questions.
Searching for Mars on Earth, oceans on Mars, possible past life, that's pretty cool. Hopefully we'll all have a chance to visit the red planet in the near future. Now for a broader look at life outside Earth, CU Science Update's Damm Muri sat down with Associate Professor in Geology Stephen Mojzsis to talk about his research and the possibility of extraterrestrial life.
You know, when I came to the University of Colorado at Boulder almost 10 years ago now, to join the faculty of geology in the Department of Geological Sciences, where I'm an associate professor of geology right now. I came here with a skill set that was a little bit different from other people entering a normal geology curriculum. I had background in biochemistry, astrophysics, geochemistry, and geology and mineralogy. So you may think that these things are eminently unrelated, but there's a common thread that links my research, and that is, when could conditions conceivably emerge on a world like ours that is conducive for life? And the reason that I'm interested in extraterrestrial life, of course, is that I use, as a geologist, the Earth as a natural laboratory for investigating questions such as, what were the conditions wherein life began on our planet? And how can we investigate the ancient geological record and apply it in our search for life elsewhere?
What have your findings been so far?
Well, we've had an exciting run, you might say. Before coming here, I was involved in a project that asked the question, if we could find the earliest rocks of sedimentary origin, meaning materials that were deposited in a milieu that was conducive to life, such as liquid water was present, energy was present, and molecules conducive to biological activity like organic matter and various salts and minerals, then we may be able to search these rocks for chemical and perhaps isotopic clues to determine whether or not life was present. Now we did that, and we pushed evidence for life on this planet to very close to 4 billion years ago. And that's interesting, not just because we're trying to get in the Guinness Book of World Records or something, but more precisely to try to get a handle on figuring out how easy is it for life to get started on a planet like ours. And the basis of that viewpoint is that the earlier something appears in a system, the more likely it will appear in similar systems elsewhere.
Is that sort of how you search for life on other planets then?
Well, our baseline for searching for life anywhere is what we know from here. For instance, we can walk out the door of this studio and see plants growing and collecting sunlight and transforming that energy along with gases and minerals in the soil to woody tissue. But that's probably not common in the universe.
No.
The kind of life that's common in the universe, we think, we have no proof of this, but this is the starting idea, is microbial, what most people consider are germs. Microbial life, like bacteria and other organisms that you can't see with the naked eye, but when they're present on a planet, can induce profound chemical changes. See, when life is in the room, the environment is completely different compared to if you have a sterile system. And that's why we do what we do.
Okay.
We want to know when, how, and why was there a transition from non-life to life at some period way in the deep past of Earth history. Now, it's amazing, but in hindsight, it's really not that much of a surprise. Because most of the life that we know, right, animals and plants and fungi and so on, lichens and other things on rocks, that's the life that we can see. But it turns out in the vast panoply of life on our planet, that's a small sliver, a veneer really, of the true extent of biological diversity.
Yeah.
So if you were to think of the diversity of life sort of like an apple pie, the animals, plants, and fungi would be this little tiny wedge of the apple pie, and everybody else are microbes. Organisms living in soil or in seawater, and even on bigger organisms like us and sequoia trees and such things.
So that is what a planet's habitable, right?
When a planet is habitable, people or organisms, living things can live there. But here's a funny thing. I'm going to take your idea and I'll switch it around a little bit.
Okay.
You know, you can be habitable, but it doesn't mean that something's living there. This is the greatest mystery of science. What is the origin of life? We don't know. We know that life is composed of chemical compounds put in a particular complex arrangement, and that complex arrangement generates information, and that information contained in our DNA and RNA is transmitted through the generations, evolves, mutates, changes, until you get sort of the evolved biological systems that we have now. But we don't know what that step was.
No.
And this is actually quite exciting, to try to search for clues on what those steps needed to be to get from non-living to living.
Yeah. So when it comes to life on other planets, then how far away do you think that we can? It is until we have contact with someone as big as our beings, perhaps.
Communicate with us, perhaps?
Yeah.
Well, that would be an easy way to go about it, because you simply turn on your radio or you have listening stations, as we do. So there's the Allen Telescope Array, for instance, in Northern California, that is basically an eavesdropping means of looking for civilizations that transmit in our galactic neighborhood. However, you know, there is a problem with that. It presumes that we know what we're listening for. It presumes that there are civilizations nearby that are transmitting outward rather than inward towards themselves. It presumes that even if we get a signal, that we'd somehow be able to tease it out of the noise of the great cosmic background. So that is a very hopeful enterprise. And it's kind of like playing the lottery. You know, there's the only way that you can win is if you play. If you don't ever buy a lottery ticket, forget about ever hitting the jackpot. So that, I think, is the basis for this search for extraterrestrial intelligence project. There's another way, however. We could make use of the fact that these microbes that I was talking about, although they're tiny, they're very powerful agents for change on a planetary scale. Every time you take a breath in, you know, breathe in. Well, it feels good, right? Well, that air contains about 21% oxygen. And that oxygen came from the long, toilsome work of blue-green algae and other microorganisms in the oceans and soils. You know, they're modern, well, I wouldn't say modern, they're recent descendants are the land plants. But ultimately, a land plant is just a very complicated community of microorganisms that now work together into a single being. So we can look for such clues remotely using telescopes great big orbiting telescopes orbiting the Earth or perhaps out in the asteroid belt where it's dark and away from sunlight, looking towards other worlds and seeking for signatures of chemical change in the atmospheres of this world, induced by these little microbes. It happened here.
So why wouldn't it happen somewhere else?
That's the thought.
That's the thought. And what would you say would be the biggest breakthrough in your career?
Up to today, I would say that the biggest breakthrough that I have experienced working with my team of collaborators is the determination that our world has been habitable for about 90% of its history. Since soon after the Earth formed, it appears that things have settled down so quickly that an atmosphere and a crust and a watery veneer was established rapidly. Now, this is just the sort of thing that anyone who is interested in searching for evidence of life elsewhere wants to know about. If it happens quickly here, like within 150 million years of the Earth's formation, so that the stage is set, whether or not the actors were present, we don't know, but the stage was set for a habitable world early and quickly. This is evidence that we first reported in 2001, and since then we and our collaborators here at the University of Colorado at Boulder, but elsewhere at University of California, Los Angeles, and other institutions, have shown that, in fact, the earliest part of Earth history was eminently suitable for life. Now, what's ahead? Many people talk about the good old days. The good old days when there were a lot of discoveries to be made and those were exciting times. We're in the good old days now. This is the golden age of exploration in science, particularly with respect to the interaction of the solid Earth with biota, with organisms, with life. And that's what geobiology is. How does life and the activity of life affect the evolution of the Earth? And how does the evolution of the Earth affect the evolution of life? These two ideas brought together create a new kind of science of looking at our planet like that blue marble that the astronauts viewed from the lunar surface as an encapsulated physical chemical system that is in totality evolving. By understanding that system, we can understand the likelihood of life on Mars, life on or within icy moons around gas giants like Jupiter or Saturn, and then the possibility for life around other stars. Because, not all stars are the same age.
No.
In fact, our closest star, Alpha Centauri, is somewhat older than us. So if it had a solar system, what would our solar system look like 1.5 billion years from now? Maybe Alpha Centauri, our closest neighbor solar system, could provide clues about that. And then looking beyond at younger stars, what will we see? I think we're on the threshold now of seeing a zoo of possibilities, and we're in for a lot of surprises. I look forward to it.
Early life on Earth could mean there's plenty of life elsewhere in the universe. The search for ET is picking up speed, and CU researchers are leading the way. Thanks for joining us here at CU Science Update. Be sure to check out our other video podcasts on iTunes. And remember, keep looking at the stars, because they may just be looking back at you.